Hello students, in this video we'll discuss extending the Laplace transform to a function in the complex plane and begin our discussion on how we would go about finding a formula for the inverse Laplace transform. Let's recall from our ODE class long ago that the Laplace transform of a function f of t, where t over here, t is greater than or equal to 0, that's the domain of these functions, is f tilde of s, and that's the integral from 0 to infinity of f of t e to the negative st dt, right? And when we studied Laplace transforms, we said that these integrals will converge so long as s is what? So long as s is bigger than some number a, right? So these integrals converge as long as s is bigger than some number a, right? Some real number a, bigger than or equal to 0, right? Okay, and so this a, of course, is called, like, what's in old books, it's called the abacus of convergence, right? Or the abacus of convergence of this integral, family of integrals over here, right? Now, the beautiful thing is that what will happen over there, I know that these will converge if s is bigger than a, right? So now I want to extend this Laplace transform, extend this to the complex plane. As follows. Okay, and so I'm going to consider, let z be a complex number. Let's do it like this, actually. Let's just say, let's consider the set of z in the complex plane such that the real part of z is bigger than a. Okay, good. Then define for any z in the set f tilde of z to be what? To be the integral from 0 to infinity of f of what? F of t. That makes perfect sense. And then e to the what? Then e to the negative zt dt. Okay? Now, why will this integral converge? Okay? Let's estimate this. So we can estimate the integral from 0 to infinity of f of t e to the negative zt dt is less than or equal to, well, I'm going to put the integral on the inside, absolute on the inside, so I'm at absolute f of t, right? And then what? And then we're going to have a e to the what? E to the negative real part of z times t, right? And then what? And then times e to the negative imaginary part of z t with an I dt. And this over here is what? That's unimodular, right? So this is less than or equal to the integral from 0 to infinity of modulus of f of t times e to the negative what? Real part of z is bigger than a, so this is less than negative a t, right? And of course, these things are going to converge, and provided that we're in this region over here, right? So provided we're in this region, dt, and that's less than infinity, okay? Excellent. So in other words, this integral over here is going to make perfect sense over here. It's well defined as long as we're in this half plane. Excellent, okay? That comes from this unimodular thing, doesn't change anything at all. It basically just turns into a Fourier transform in some sense. Good. And so now I have a complex extension, so f tilde of z, which is the integral from 0 to infinity of f of t e to the negative z of t dt, agrees with what? Agrees is equal to f tilde of s if z is equal to s, right? If z is equal to s is equal to r. So by the identity principle, this is a genuine extension, right? So by the identity principle, this is an actual extension. It's actually from the identity principle and Morera's theorem, right? Because if I integrate this over a triangle, that's going to be 0 by Morera's theorem, right? So the identity principle and Morera's theorem. Okay, so two high-powered results actually. The identity principle and Morera's theorem allow me to extend the Laplace transform to the complex plane. Okay, now of course the calculations work exactly the same, right? The calculations are identical actually, right? So if I was to do this problem over here, what would be the, so here's a classic example, right? If f of t is just equal to 1, right? Then what will I do over here? Then what will my complex Laplace transform be? My complex Laplace transform, f tilde of z, is going to be what? Is going to be the integral from 0 to infinity of e to the negative z t dt, right? And that's going to give me what? Well, just integrate and get 1 over z, right? So this implies that f tilde of z is equal to 1 over z, right? Oh, that makes perfect sense with what we know about the Laplace transform of 1. We know the Laplace transform of 1 is 1 over s, right? So what's the consequence of this? An immediate consequence of this is the following. You get a proposition. The formulae, right? Valid for the Laplace transform of real valued functions remain true in the complex case. Okay, all your favorites, right? All your favorite results are true, right? So for example, I can say if f of t is equal to what? Is equal to sine of t, then what does this imply? This implies f tilde of z is what? F tilde of z is going to be 1 over z squared plus 1. Same formula. It has to be the same formula just by the identity principle over here, right? So in other words, this function over here is the Laplace transform of the complex Laplace transform of sine of t, and all the other formulas remain exactly the same, right? So what we're going to do now in the next couple of videos is we're going to say, okay, well, if this gives me a formula for the Laplace transform, we remember back when we were doing Laplace transforms and said, how to do the inverse Laplace transform? We had all sorts of things like say, oh, well, the inverse Laplace transform of simple stuff can be computed directly. We use series to do some of the inverse Laplace transforms. We basically use partial fractions to do some of them. We use convolutions to do some of them. So all of these things, series, convolutions, right? And of course, the power functions gave us the series. So we have series and convolutions, gives us a hint that there's something to do with that series are involved with inverse Laplace transforms and integral operators are involved with inverse Laplace transforms. So now what we can do is we can use our representations of holomorphic functions on the right half planes to write the inverse Laplace, to write the Laplace transform as an integral over a line. And then what we can do is we can say, well, now I can take that line and then encapsulate all the singularities of the extended function, use the residue theorem to write the inverse Laplace transform as a sum, as a series of residues. So in further videos, we'll extend that idea to the Bromwich integral, which will allow us to compute inverse Laplace transforms using series. Thank you very much.